Hey everyone, welcome back. This is lesson 2 of our final unit this year in Math 2. In the last lesson, we talked about the Pythagorean theorem and the triangle sum theorem. Those two things helped us to find missing angles of any triangle, okay? Because remember, the three angles in a triangle always add up to 180. So to find a missing angle, you'd add up the two angles that you do have and then subtract that from 180 to find the third angle. That's the triangle sum theorem. The Pythagorean theorem was finding the missing side of a right triangle. So if you had two sides of a right triangle, you can use the Pythagorean theorem to find the third side. So remember, that was leg squared plus leg squared equals hypotenuse squared. But here in this lesson, we're going to be talking about something called similarity. Now, we're going to kind of brush through briefly through what similarity is, and then we're going to use it to find missing sides of triangles, and not just right triangles like we could with the Pythagorean theorem, but any triangles as long as we have similarity. So you saw the first part of those notes there, but let's go ahead and get started. Again, similarity, and our goal is to be able to find the missing side lengths of a pair of similar triangles. Well, what does it mean to be similar? Similarity means, okay, there's two parts to similarity, two parts to the definition. Number one, two objects are similar if their corresponding angles are congruent. And number two, their corresponding sides are proportional. What in the world does that all mean? Well, let me kind of give you a diagram here. So if I have two triangles, let's say, it could really be any shapes, but let's just say I've got two triangles. So here's triangle one, and let me go ahead and scroll this over here so you can see it a little bit. So there's triangle one, and let's say that this is going to be triangle two. Now, these triangles are similar. They're very, very close to being similar. They're not going to be exact because my drawings aren't perfect. But the idea is this. The first part of the definition, remember, said that corresponding angles are congruent. So that means the three angles are the same, or the three corresponding angles, which means the angle here, this angle, how wide this angle opens up, needs to be the same as how wide this angle opens up, okay? Now you might say, well, that angle is different than that one. No, it's not. It appears to maybe be different because the length of the sides, right? These lengths are longer than these lengths. But when we're talking about an angle measurement, we're not talking about how long something is. We're talking about how wide it opens up, okay? So we've got one set of corresponding angles. And so if this angle is congruent to this one, so now we have two sets of corresponding angles, and then this angle is congruent to that one. Now we have three sets of corresponding angles, okay? Corresponding congruent angles. So that's the first thing that it means to be similar. If you have three sets of corresponding congruent angles, then you can say, well, I think they're similar. We would look for one more thing. The corresponding sides must be proportional. What does that mean? That means there's a scale factor to them. Or we could say that there's one of the side lengths here, all the side lengths here are being multiplied by some constant number to get to these lengths here, or vice versa, okay? But let's go through kind of more of a basic way of seeing this, just to help us understand it a little bit. Whoops, as I'm moving things around here, wrong box. Let's try and understand it through just basic terminology. Basically this, similarity means that two objects are the same exact shape, but different sizes. Now they could be the same size, they could be the same shape and the same size, and they'd be similar. They'd also be congruent. But basically, similar shapes are two objects that are the same exact shape, but different size. That doesn't mean two triangles. Any two triangles will work. It means that the two triangles must look exactly the same. just one is bigger than the other. So it's like zooming in or zooming out on an object. When I zoom in, I see a bigger picture. When I zoom out, I see a smaller picture, but they're the same picture. So they're similar in that way, okay? So that's what similarity means, okay? So here's one triangle. Here's another triangle, okay? So this is an example of this, okay? Now, are these objects, are these triangles similar? Well, do they look like they're the same shape but different sizes? Maybe. Let me go ahead and turn this one a little bit, okay? And maybe I'll turn it a little bit more. And maybe a little bit more. And maybe I'll move it over here so we can see it a little bit closer. Maybe it looks like it needs to get bigger, right, to make it match, okay? Maybe we need to move it a little bit closer so we can see how closely these look. Now these look pretty close to each other. They don't look exact yet, but let's see here. So let me see if I can line it up pretty close just so you can see the difference between them. Okay. Oh, come on, fingers. They're not wanting to work today. Okay, so you can see that these two triangles are actually the same exact triangle. It's just one I shrunk down a little bit. So you can see it here. Oops. Oh boy, I messed up. Well, you can see as we moved it along, we can see that one triangle was the exact same shape, but different sizes. And so I'm going to take that one and I'm going to move it back over here. So they're the same exact triangle. I just moved it around. I rotated it a little bit and I did what's called dilating it. So I made it bigger so that I could see that they're actually the same exact triangle, just one triangle is bigger than the other. Okay. So let's go ahead and take a look at an example of one of these problems where we want to find the missing side links. Okay. So let's see here. In the first triangle, the smaller triangle, we can see that we have the side length of 7, a side length of 4, and a side length of y, 7, 4, and y. Now somebody might say, well, I can do the Pythagorean theorem to find y. Remember, the Pythagorean theorem only works when it's a right triangle. So we would need to know that one of these angles is a right angle, a 90-degree angle. And some might say, well, that looks like a 90-degree angle. Yes, it does look like one, but that doesn't mean that it is one. It could be 89.999 degrees or 90.0001 degrees. If it's not exactly 90 degrees, then you can't do the Pythagorean theorem to find a missing side. So we have to resort to something else. Well, we notice that these two triangles are similar to each other. Why are they similar? Well, they appear to be the same exact shape, but different sizes, right? This one's smaller, this one's bigger. But more than that, we can see that the three corresponding angles are congruent. And since those three angles are congruent to each other, we know that these triangles are similar. So now we can solve the missing sides of these triangles. And we do that by setting up proportions, just like I said in the last slide. The side lengths are going to be proportional to each other. So what we do to do this is we pick one of the sides from one triangle. So in the first one, I'll start off with 7 inches, right? Those two lines just mean inches. They're just a unit of measure. I'm not going to write it down. 7, and then another one is 4, and another one is y. So I listed the 3 side lengths of one of the triangles here. I'm going to go ahead and list the other side lengths of the other triangle right underneath it, So, but I want to make sure that the corresponding parts go together. The parts that relate to one another go together. So underneath 7, I want to put the 11 because you can see that the 7 is between the two angles that have a 1 little arc mark here and 3 arc marks there. This one 1 arc mark, 3 arc marks. So 7 and 11 correspond with each other. So I'm going to put the 11 underneath the 7. And then, well, what goes with the 4? What corresponds with the 4? We can see that the x corresponds with the 4. And then what corresponds with the y? We can see that the 13 corresponds with the y. So all I did was I listed the 3 side lengths of one triangle, And then I listed the other 3 side lengths of the other triangle right underneath it. Now watch this magic. I'm going to make fractions out of all of these. Okay. Now, if these triangles are similar, and they are, that means that this fraction is going to be equal to this fraction, is going to be equal to this fraction. So now I have what's called proportions, okay? Because these 3 ratios are equal to each other. We just need to make sure that corresponding parts go together. Notice I listed everything in the small triangle on top, and I listed everything in the big triangle on the bottom, and I made sure that the things correspond correctly. Now, if I cover up this last fraction, the y over 13, I can see that I actually have an equation that I can solve. And you guys learned how to solve proportions in Math 1. So how do we solve for proportions? Well, we cross multiply. So we say 7 times x. Well, what's 7 times x? 7 times x is 7x. And then that's equal to 4 times 11. 4 times 11 is 44. And so now I have an equation that I can solve, and I can solve for x. I can get x by itself. So how do I do that? Well, I divide by 7 on both sides. And so on this side, I end up with x equals. And on this side, I could write this as a mixed fraction. I could write it as an improper fraction with reduced, or I could put it as a decimal, just depending on what the question is. In this case, I'm going to either write it as an improper fraction, so 44 over 7, or I'm going to get my calculator out, and I'm going to say 44 divided by 7. And so I end up with 6.286 if I round that. So that would be a good estimation, a good value for the missing side length, 6.286. So that tells us what this length is on this side. Now we need to figure out how to find y. Well, we can use any relationship here, any equal sign here. So we could set 4 over x equal to y over 13, but I have 2 variables there, so that's not going to be easy to solve. I could plug x in, but that's a decimal, so I don't want to use that. I always want to use the fraction that I know both of. So I'm going to set this up as 7 over 11 equals y over 13. So essentially, what am I doing? I'm covering up that middle term, and I'm setting this equal to this, and then cross multiplying and solving. So 7 times 13 is going to be, 7 times 10 is 70, 7 times 3 is 21, so that's going to be 91, and then equal to 11 times y is going to be 11y. And then from here, we'll divide by 11, and then we can say that y equals either 91 over 11, or with our calculator, 91 divided by 11 is going to be 8.273 inches if I round it to the nearest thousandth. Okay, so that is how you find the missing side lengths of triangles if those triangles are similar to each other. And these triangles are similar because all their angles are congruent to each other. Okay, so that is how you do that. Here's a practice problem that I want you to spend a few minutes on trying to solve on your own. And when you are done, push play and see how you did. Okay, so what is the length of the missing side that kind of got cut off? But what do we need to do? Notice that in this case, I'm missing both of these sides. Okay, I don't know either one of these, so these are not going to be helpful to me at all. I want to figure out what x is, and I have these 3 values here. So just like I did before, in this problem, number 1, I'm going to list the 3 side lengths of this triangle over here. Now notice I only have 2, so I'm going to say 5 and 14. And then I'm going to list the side lengths that correspond with those right underneath that. So the 5 goes with the 3 because they're in the same position. And then the x goes with the 14 because they are in the same position. So we put them as a fraction and we set them equal to each other. And then from here, we cross multiply. 5 times x is going to be 5x. And then 14 times 3 is going to be 42. From here, we'll divide by 5. And so we end up with x equals 8.4. And there's no units of measure on this, so that is our final answer. Now, another way to think about this when setting up these ratios is I always start with x, okay? This is just a different way of looking at it. I always start with x, so I'll say x. And then I ask myself, so x over, what does x go with in the other triangle? What does it correspond with? So x goes with the 14, okay? Because they're both between the two angles that are congruent to each other, right? We see the one little arc mark there, the two little arc marks there. The x is between both of those. The 14 is between both of those. So we say x over 14. That will be equal to, then we go back over to this triangle because x is on top. That means everything from this triangle needs to be on top. So I'm going to say 3 over, what does the 3 go with? The 3 goes with the 5. And then we can cross multiply. Now I'm not going to do that work again because it's essentially the same thing. When I go to cross multiply this, I got 5 times x is 5x. When I multiply this, x times 5 is also 5x. Maybe I should do it. 5x. And then the 3 times the 14 becomes 42, which is exactly what I have up here. 5x equals 42. So there's a couple of different ways to look at it. Either way will work, okay? So that is the answer. 8.4 is the answer to your problem. We've got one more problem left to go, and I would like you to try this on your own. It's got a lot of little pieces to it. It shouldn't be too difficult for you. I want you to find all the missing angles and the missing side lengths, okay? So go ahead and push pause and see what you can come up with. All right, for these two triangles, we really don't have enough information at this point to find the missing side lengths. Well, you go, well, I just set up ratios to find the missing lengths. Well, yeah, if the triangles are similar to each other. But how do you know they're similar? Well, because they look like they're the same shape and different sizes. Yes, they do, but how do you know that for sure? Remember, to know that, you have to know that the angles are congruent to each other, okay? Well, what do we see? We see that the 72 is equal to the 72, so that's one of the angles, but that's not all of them. And I see the 51, well, that doesn't go with 57, so those aren't congruent, so these triangles must not be similar, so I can't find those missing sides. Well, wait a minute now, wait a minute. I can find the missing angle here because what did we learn in the last lesson? We learned that the three angles in a triangle always add up to 180. So I could say 51, as I write a 7, silly, 51 plus 72 plus x equals 180, right? The three angles in the triangle add up to 180. So that'd be 123 plus x equals 180. And then we'll subtract the 123, and we end up with 57, and that'd be 57 degrees. And so now we can see that x is 57 degrees, not because this is 57, okay? Don't jump to that conclusion. Just because you see that there, it automatically means it here. You've got to find that independent of itself, so independent of the other triangle. So that's 57 degrees. Now we can find y. We'll do the same thing. We would say y plus 72 plus 57 equals 180 degrees. And then we combine like terms, so y plus 129 equals 180 degrees. We'll subtract that 129, we get y equals 51 degrees. Okay, so we have x and y, and now we do know that these triangles are similar because I've got 72 congruent to 72. I've got 51 and y is 51, so those are the same, and then x is 57 and 57. So I've got congruent angles here. That means I can find the missing side lengths of this triangle. So let's go ahead and set up a proportion that's going to help us out. So you can pick anything you want. I'm going to pick the smaller triangle here. I'm going to say W. The next one I'm going to say is the 12.4. And then the next one is going to be 13.8. And then, oops, I said that wrong. I'm sorry. Let me start over here. W, 12.4, and 10.1. Those are the three lengths in the smaller triangle, okay? In the bigger triangle, We're going to list them again, but we want to make sure that they go together. So what goes with the W? The 12.2 goes with the W. What goes with the 12.4? Well, that would be 13.8. And what goes with the 10.1? That would be V. So we put them over as a fraction, set them all equal to each other. We know that those are going to be equal to each other because the triangles are similar, right? So now we can ignore one of these expressions and solve the other one. So I'm going to go ahead and cover up this one, the V, and I'm going to just work with this. So W times 13.8, that's going to be 13.8W, and that's equal to 12.4 times 12, 12.4 times 12.2, and I'll get my calculator out for that. 12.4 times 12.2 is going to be 151.28. And then we will divide by 13.8 on both sides. And divided by 13.8, we end up with W equals 10.962. And there's no units on that, so that's all W is, okay? So 10.962. For the other one, we'll ignore the W now, and we'll focus on the other relationship. 12.4 over 13.8 equals 10.1 over V. We'll cross multiply those. So we end up with 12.4V equals, and then the 13.8 times 10.1 is going to be 139.38. And then, of course, divide by 12.4. And we end up with V equals, calculator again, 11.240. Now, some of you are saying, why do you put a zero there? If it's a zero there, then why even put it? And you're correct. Other than to say I put the zero there to let you know that I rounded, right? I want you to know that there's numbers that came after that. But anyways, that's V. And that wraps it up, okay? So we know how to find missing side lengths of similar triangles. Yesterday we talked about finding missing side lengths of right triangles. We found missing angles of any triangles. And today we're finding missing side lengths of any triangles as long as you have two triangles that are similar to each other. If you have any questions for me, please reach out, comment below, or find me in tutoring, and I'll be glad to help you out. I'll talk to you later.